Hi there, Mr. Sutton here, bringing you this lesson on properties of definite integrals. We're going to be using these properties of definite integrals to evaluate them.
For our warm-up, let's say that we have the following three definite integrals. So we have the integral of f from 1 to 4, and they're telling us that's 7. Integral of f from 4 to 6 is 5. And then finally, we have this g integral from 1 to 4, which they're telling us comes out to 3. Let's further suppose that we have the following graphs. So we have f right here. So here's the integral from 1 to 4 with the area of 7, integral from 4 to 6 with an area of 5. And let's say we also have a graph of the g function. Integral from 1 to 4, again, the area is 3 on that one. Using these graphs, see if you can figure out the following definite integrals here. So there's a bunch of them here, but pause the video and see how many of these you can reason out just using the areas in these graphs.
All right, let's see how well your intuition worked out on these. So for this one, probably the graph of the f function would be the most relevant here. And it says, let's see, we're integrating from 4 to 1 for f of x. Looking under the graph between 4 and 1, or 1 and 4, it looks like there's an area of 7. However, if you're going from 4 to 1, because that's what our integration is doing, 4 is the lower limit of integration, you're essentially integrating backwards. Now, when you integrate backwards, it's pretty much like having a negative base and deleting area instead of adding area. So this would end up being an area of negative 7. In general, when you switch the limits or integrate backwards, you're negating the overall value of the integral. So if the original integral is 7, the backwards integral is going to be negative 7. For our second example, we had the integral from 1 to 1 of f of x dx. So here is f of x again, and we're not going from 1 to 4, we're going from 1 to, wait for it, 1. How much area is there in there? If you're not really sure, consider this. You're going from 1 to 1, so you have a base of 0. 0 times anything is going to be 0. So if the limits are the same, then your area is going to be 0. You have an infinitely thin just kind of sliver here. So that's all going to come out to 0. For our third example, we want the integral from 0 to 4 of g of x dx. So here's the graph we had for the g function. This tells us the area from 1 to 4 is 3. But how about the area from 0 to 4? We actually don't know how much area is in there. So we don't have enough information to come up with an exact integral. Now, having said that, we can say a little bit something here. This is positive area, whatever it is. So that means that the integral from 0 to 4 must be greater than the area from 1 to 4. So we know that this is going to come out to a number that's greater than 3, but beyond that we can't really say. For this next example, we have the integral from 1 to 4 of 2 times g of x dx. So looking at our graph of g, if you're multiplying 2 by that integrand, you're essentially doubling the height of all these rectangles, giving you a function that is twice as tall in every place. Well, if the function's twice as tall, then the area is also going to be doubled. So total area of 6 if we look at this just on a graph here. Now looking at this more algebraically, another way of doing this is you can take out or put in constants to the integral. Since you're essentially just doubling all the heights, it doesn't really matter whether you do that before adding up all the rectangles or after. So we could consider this to really just be 2 times the integral from 1 to 4 of plain old g of x, which is just going to be 2 times 3, or 6. For example 5, it looks like we're adding 2 different functions inside the same integrand. So how can we handle this? Visually, what are we doing? What we're essentially doing is we're taking everything that f is doing and adding it to everything that g is doing between 1 and 4, like so. So here we go, and let's just spin that around a bit. There we go. So we have this big combined area that f plus g of x represents. Now, how much area is this? Well, visually, we can very clearly see this comes out to an area of 10. But how could we have gotten that without a picture? So if you're just taking these individual areas and adding them together, another way of saying that is that you could have actually split up this integral into 2 different integrals, calculated them, and then just added them after the fact. So whenever you have addition or subtraction, you can actually split that up into 2 integrals. So we could have expressed this as the integral from 1 to 4 of f plus the integral of 1 to 4 of g of x. And then that's just going to be, let's see here, we got 7 plus 3 adds up to 10. So this is one way of using the addition, subtraction, split it up property. Another way you can actually use it is you can merge integrals that are being added and subtracted if, like these two integrals we just came up with here, if they have the same limits of integration. Now this might be useful to merge these back into a single integral if you could somehow combine these two integrands. Maybe there's some like terms or something you could combine. So this one works both ways.
So at this point in the lesson, we've got a few techniques under our belt. Let's take a look at this example here. Now, if you didn't know what to really do on this one when we started, pause the video and see if you can give it another shot in light of our newfound knowledge about integrals. All right, let's see how this went. So there's two rules that will be helpful here. We can definitely split up this integral using subtraction. So we're going to have two integrals from 1 to 4. And we can also use the basically the popping out rule of integrals here. We can bring this 2 outside one of the integrals and bring this 3 outside the other integral. So I can have 2 times an integral from 1 to 4 of the f function minus 3 times an integral from 1 to 4 of the g function. Well, what is integral of 1 to 4 of f? That is, at least in this lesson, 7. So we've got 2 times 7, and over here we have minus 3 times 3. So that'll be 14 minus 9 gives us 5.
For our seventh example, we're trying to find the integral from 1 to 6 of the f function. So visually, here's what's going on. We have the area already from 1 to 4, and if you look at the original graph, we actually also had this other area from 4 to 6 for the f function. Well, what is the area from 1 to 6 going to be? We can see pretty quickly just by looking at this graph that we're just adding these two different areas together, and since it's the same function and there's no space in between, we know that all of this area and all of this area gives us the total of 12. Now how can we come up with that more algebraically? So algebraically what's going on here is something called the additivity property, which says that you can add or subtract integrals that have the same integrand, so they both have the f function here, and they have one limit in common. For example, these two areas share this limit of integration here, this 4 right here. So here's the general formula for the additivity property. If I have an integral from a to b, like the integral from 1 to 4, and another integral on the same function from b to c, that would be corresponding to this 4 to 6 integral here, then we can just merge these into a single integral from a to c, in this case from 1 to 6. So this is a useful property if you have integrals, again, that have that one limit in common. Looking here, they have a b here and a b here. That tells us that these are visually just right next to each other. One is just a continuation of the other, and we can just add that area in. Now there's another direction we can go with this property. You can actually subtract as well. In this situation, let's say we have an integral going from a to c, like the integral from 1 to 6. And you want to subtract the integral from b to c, like 4 to 6. Well, that's just going to leave you the other piece of that bigger integral. So we could say a to b in this case. So there's a few directions you can go, but it really just boils down to adding and subtracting areas, parts versus wholes. Now, in this case, we're just given a single integral, not two integrals. But yet another application of this additivity property, it's got a lot of things we can use it for, is you can unadd an integral into two integrals that we already know the area of. For example, this integral, we don't know the area from 1 to 6, but we know the area from 1 to 4 and the area from 4 to 6. Since these two different integrals have the same limit of integration, they both have this 4, we can split this integral up into these two integrals, like so. We've got the area from 1 to 4 and the area from 4 to 6. Now it's important to note that this integral here, this second integral, has to begin where the other integral ends. If we had 1 to 4 and then 6 to 4, that wouldn't quite work out, because then we'd be going backwards with this second integral. But we do know that these integrals are 7 and 5 respectively, so we can add them up to get that area of 12 that we already kind of figured out visually. For our last example, we have the integral from 1 to 4 of f of k dk. We don't know anything about this. We do have another one that looks kind of similar, though. this one up here that has f of x dx and the same limits of integration. So what's the relationship between these? Well, it turns out they're actually the exact same thing. This variable in here, this k and this x, these are called dummy variables. They don't have any special significance on their own. They just have to match whatever your differential is, and they basically take care of assuming values while your integral is doing its thing. But it doesn't change what the integral does. It just changes what you're calling the placeholder. So changing the variable of integration then doesn't actually change the value of the integral. This expression and this expression up here are exactly the same value, which is to say 7. So that's it for definite integral rules. The key on this is getting lots of practice using these. Until next time, this is Mr. Sutton signing off.